Hello everyone, welcome to this second presentation provided by Carbon Guildford, and the subject is carbon reduction at home from the Green Your Home zone. This is the second presentation in the group, and this one focuses on existing heating systems and efficiency improvements. And we thought this would be highly relevant in the context of not only our carbon reduction aspirations, but of course the current escalating fuel price impact. So my name is Farquharson. I'm a local Merrow resident and have been since 1985. Professionally, I'm a chartered environmental and building services engineer. And as I've mentioned before, back in '73 when I did my bachelor's degree, my project was a solar heated house. And it's really interesting to be back focusing on energy reduction, sustainability, and our goal of net zero 2050. So welcome. You recognise this image of the Green Your Home zone down at 0 in Guildford, and we will be progressively populating this with more information, examples and samples of some of the technologies and solutions that you should consider. So just a quick thought about targets. Targets set by government, local authorities will not save the planet. Why bother with your existing system? Well, most of us can't or won't throw away our gas boilers immediately. In 2022, we've already seen and we'll see gas price escalation and clearly a very volatile market. However, I'm firmly of the opinion that many systems, certainly ones I look at, are operating suboptimally, and improvements can be made. It may be over the years that there have been additions and adaptations that are not well documented, not well controlled, perhaps poor installation quality, and systems may be suffering from poor servicing and contamination such as sludge in the system, rendering parts of the network, the piping, radiators, inefficient or poorly served. I refer to this Surrey Climate Commission summary a number of times, and the zone I want you to look at in this graphic is the one highlighted in red, which focuses on housing energy, housing carbon emissions, and they are extremely significant. So around a third of the direct emissions to the environment in Surrey. So there's certainly something to go at here. So my agenda in this presentation is as follows. I'll talk about a few critical safety matters, particularly if you're thinking of DIY approach, and also look at the basic energy units that you will bump into when you're looking at aspects of your system or your energy consumption. We'll look at the importance of understanding your heating system, so that's the boiler itself and its function, the heating system design and how it's controlled. I'll go through a number of potential energy saving measures, including heat loss reduction, proper service and maintenance, and the function and operation of the controls. Finally, I will review the really important aspect of measuring the performance, monitoring the performance, so you get some feedback. This message is always worth reinforcing. Don't forget the fabric first approach. So before we start doing anything about investing in a heating system, for example, maybe updating or changing it, let's understand and address the fabric of our building. Because if it's leaky, whatever we do will still release heat into the environment. Now, the roots of heat loss are air leakage, so that's drafts, through the roof, windows, walls and the floor. Now, understanding your building is really important because some of these may be easy to achieve, improvements too, and some will be much more difficult. What we know for a fact is that loft insulation is the cheapest, easiest and quickest improvement that can be made. Drafts are really difficult to measure and determine. And I've just put this image up, which is of the current building regulations air tightness test that would be applied to a new building. Now these are going to get more stringent with the new building regulations, but the method fundamentally involves placing a dummy door on the property, and this has a fan in it which sucks air out of the building, and at a certain negative pressure you measure how much air is flowing out, and this is an indication of the inward leakage. And there are set acceptance criteria based on the size of the building and various other attributes, and a pass would have to meet the acceptance value in these criteria. Gas and electrical safety require involvement of qualified, certified, competent personnel to undertake the work, whether that's electrical contractors or gas safe registered operatives for working on boilers and gas systems. DIY would not be acceptable, and you may end up with an installation which is not certified and tested as being satisfactory. So let's move into the meat of the presentation, some important energy related units, and these are important to understand maybe some things to do with your installation, your heating installation, or the bills you receive from your energy company. So generally, energy rate or power is measured in kilowatts, and a kilowatt is a joule per second. So I have a 1 kilowatt electric fire, that is the power that is delivered by that device. Energy quantity is measured in kilowatt hours. So your 1 kilowatt electric heater working for 1 hour consumes 1 kilowatt of energy, and your meter would measure that and you would pay for that unit of energy. Gas is a little different in that, of course, it is a compressible substance that comes down the pipe, and the measure of gas on your meter is meters cubed of gas, so cubic meters of gas. Your smart meter will probably be calibrated in kilowatt hours, and the heat available from a cubic meter of gas in kilowatt hours is based on the calorific value of the gas and the pressure or density of the gas delivered. And a pretty close approximation would be 1 cubic meter of gas times 11.36 would give you the number of kilowatt hours of energy held in that gas. Electricity is a little simpler. Consumer and smart meters are calibrated and measure in kilowatt hours, so quantities of energy. Temperature, in the context of what I'm talking about, I will refer to degrees Celsius, which are the same value as degrees Kelvin. Then one aspect of our buildings that becomes really important when we want to estimate heat loss through a component, a wall, a window, roof and so on, is the thermal transmittance of the structure or the building element. This is called the U value, and it's used to estimate the heat loss through the building fabric, and the units are watts per square metre of that element times the temperature difference between the inside and the outside. We can then aggregate all the heat losses from a space and use this as a basis for sizing individual radiators in a room, and then the boiler system or the heat source system necessary to provide enough hot water or energy to those radiators. So I now want to talk about understanding your system. There are two basic system types that we'll find in most of our houses today. And the first one is what we call a heat-only system. And here the boiler is a heat source for space heating and a domestic hot water storage cylinder, a heat-only system. The second is a combi system, and this is a heat source for space heating and a direct on-demand provision of domestic hot water without the necessity to store. And then related to these two systems, we need to recognise that there are two ways of filling and dealing with thermal expansion. We can have open gravity fed systems with a feed and expansion tank in the loft, or we can have closed systems, pressurised, usually from the mains water service, with an expansion vessel to deal with the expansion and contraction of water in the system. Then we have two boiler types, conventional boilers and condensing boilers. And condensing boilers are mandatory today for all new boiler installations, including boiler replacements. So it's good to have a system diagram. I always think this is useful to understand your diagram and help you think about how you might make modifications and improvements. So if we look at the combi boiler diagram, and this is in a very simple house representation, here we see the combi boiler probably in a kitchen cabinet with a time programmer and a room thermostat, and this serves a heating system, copper pipework, distributed around the house, through which water flows, goes through radiators to liberate heat, to heat the rooms, and then returns back to the boiler. Now the combi boiler also has the ability to deliver domestic hot water, sometimes called hot water service, directly to taps on demand, and the boiler will fire if necessary to deliver that hot water on demand, and when the taps close the boiler shuts down. The second diagram I want to show you is in the heat only system, and in this case I'm illustrating the classic feed and expansion tank and cold water storage tank in the loft. These may not be necessary in slightly different arrangements of these systems. But in this case, the boiler, which could also be mounted in a kitchen cupboard depending on its size, provides a primary heat source that goes both to the heating circuit and to the hot water cylinder. And control valves divert the heat source to one or other of those sub-circuits, or both at the same time. In this case, domestic hot water is drawn from the hot water cylinder and doesn't require the boiler to fire specifically to deliver the water. The boiler will fire depending on a time clock and when that cylinder needs topping up with heat. Now the boilers I've shown you today will have to be condensing boilers, and it's really important to understand how these work because there are some adjustments you should make to get optimal performance. So a condensing boiler, and the reason we have them and why they are prescribed in the building regulations, is that they are around 25% more efficient than a traditional non-condensing boiler. So there are two key parts of the condensing boiler. The first part on the left-hand side of this diagram is the primary combustion chamber, where the gas is burnt and the hot gases heat the water. The second part is where we extract heat, and this is on the right-hand side of this diagram, from those combustion gases. So they leave the combustion chamber hot, and they pass through a second heat exchanger where the temperature drops. So first there is sensible heat temperature reduction, and then the flue gases are condensed, which is largely water with some contaminants, which can be acidic, and this removes the latent heat in those combustion gases, and the condense goes down the drain. Really important that the condense flows away and that the condense pipe is not blocked. Now, for this to work effectively, the return water temperature from your heating system needs to be around 40 or 45 degrees. If it's too high, you will lose all that condensing efficiency, that condensing energy recovery. Let's just have a quick look at some different heating system operating temperatures. So usually you will see about 20 degrees difference between the flow of water from the heating source and the return back to the heating source when the system is working at full load. A traditional non-condensing boiler would operate between 80 flow, 60 return, maybe 70-50. A condensing boiler should be working at 65-45, and a combi boiler the same. But when you go to a heat pump, so a most efficient heat pump will be more like 45-25. There are some high temperature heat pumps, but they have much less efficiency. Now I'm going to deal with heat pumps in the third of the talks when we look at low carbon heating sources. Now radiators, this is really important component of our heating system. So you're all familiar with a radiator with some control valve, a manual or thermostatic radiator valve at one end, and a balancing or lock shield valve at the other end. Now radiators, in spite of their name, do not only radiate. In fact, a majority of radiators will produce 80% of their heat through convection and only about 20% through radiation. Now in a radiator we need to consider the mean water temperature, so that's the mean between the flow and return, and this will be quoted in radiator technical catalogues. As the mean water temperature drops, the difference in temperature between the radiator and the room drops and the output of the radiator reduces. And this can be quite significant. So let's have a look at a couple of examples. So the important thing is the delta T, or temperature difference, between the mean water temperature and the room. If we assume the room is at 20 degrees centigrade and the mean water temperature drops from 70 to 55 because we've just changed our conventional to a condensing boiler, we could see the radiator output drop by 30 to 35%. If it drops from 55 to 35 degrees C, the mean water temperature, because we've changed to a heat pump, the delta T falls from 35 to 15 degrees C, and the output of the radiator could drop by 50 or 60%. So changing your heat source may require a significant re-evaluation of the heat output devices. The next element of a system are the typical controls. So the boiler, first of all, the heat source, will normally be controlled by a time clock and flow temperature and burner control. So older boilers are on-off, more modern ones have modulating output burners. The demand for heat, that's how the heat is delivered into our rooms in our house. The heating is controlled usually by a thermostat, a wall-mounted thermostat, which may be on its own or in combination with thermostatic radiator valves. And I'll talk more about those later. And then we have a hot water cylinder, which is controlled by a thermostat on the hot water cylinder, or if it's a combi boiler, the direct use of hot water and the control of temperature is part of the boiler control system. So that's all I want to say about system configuration and the critical system components. I now want to work through some potential energy saving improvements that you might be able to take. So first of all, reducing heat losses from your system. And there are two approaches I want to identify here. Insulate exposed pipework or areas of pipework where you do not want that heat to escape. I now want to mention the use of reflective film placed behind radiators and between radiators and an outside wall. This measure, which is very cheap to fit, often forgotten, can significantly reduce the radiated energy loss from the back of a radiator. I now want to move on to maintenance of the boiler and system care and maintenance. I produced here a boiler service checklist. You might find this useful to use with your boiler service contractor. So you will see it covers a whole number of things that are safety related and functionally related: carbon monoxide tests, combustion tests, gas pressure tests. And this is particularly relevant as large parts of Guildford have been undergoing gas main replacement, and this is how they slide a new plastic pipe inside the old failed metal pipes. Inspection of internal components for corrosion and damage is really important. A combustion test with the flue gas analyzer, checking safety devices, inspection of the pipework, inspection of the electrical installation, and looking for any corrosion or leaks, particularly from the condenser section of a condensing boiler. And cleaning boiler parts, including filters and the combustion chamber. The distribution heating system also needs service, and it may periodically need cleaning and sludge removal. It should be filled with a corrosion inhibitor. You may need to vent the system, particularly radiators, to ensure they're full of water, not air. And you may want to clean or add a filter if it's not installed, and check the feed and expansion tank or pressurization system and make sure that it's working correctly. Magnetic filters are recommended, and here's one that's been retrofitted to an existing system. to help prevent sludge and debris from the system building up, particularly in your boiler or your radiators. These are most commonly located on the return back to the boiler. I now want to move on to controls. I've talked a little bit about the controls of the boiler itself and of a hot water cylinder, but I want to look a little bit more about the controls of the heating system, whether that's a simple thermostat, a smart thermostat, thermostatic radiator valves, or more sophisticated zonal control system. Most of our boilers just have a plus minus knob. You can see this on the right hand side of this boiler, that allows me to turn the boiler up or down with no values. Some boilers do have some temperature setting values, so you can adjust the output to get the right system temperatures. If your boiler does not have a digital instrument on the front, I suggest that you add thermometers to the flow and return in your system, and these can be quite economic clamp-on type devices, as you can see on the right. Set your boiler operating temperature. So certainly if it's a condensing boiler, the flow should be around 65 to make sure the return comes back at a condensing temperature. If you don't do this, if you have the system working at a much higher temperature, you may not get the condensing energy recovery. Hot water cylinder temperature. Again, this should be around 60 degrees, and this helps to inhibit Legionella growth, and it's an adequate temperature for most of our personal washing, showering needs. So make sure the thermostat is correctly installed on the cylinder, that it works, and the immersion heater is off. You might want to consider a dual coil cylinder for taking advantage of solar thermal, or an alternative electrical heating source for photovoltaic, if you were considering replacing your cylinder to future-proof it for changes you might make later. So just a diagram here of a classic solar thermal arrangement where you have two coils in one cylinder. So let's move on to space heating control operation options. So first of all, we've got the operating patterns, where you turn a system on only when you want heat, or you have it on always at set temperatures, or C, you have it on all the time with setback and occupied temperatures which are programmable. Which is most economic? No simple answer, I'm afraid. It depends on a lot of things, particularly occupancy pattern. So if the house is only occupied first thing in the morning and in the evening, and it's a poorly insulated property, then it's likely that option A would be best. Options B and C could apply to a different working pattern and to better insulated properties. So now we can think about space heating control configuration options. And there are a number of these possibilities. First, A, a single simple room thermostat with a time clock and static balanced radiators. B, simple thermostat again with time clock, but now we add thermostatic radiator valves to the individual radiators in each room, giving a degree of local control. C, single programmable room thermostat with thermostatic radiator valves. D, single programmable smart room thermostat, maybe with some external access via the internet and your smartphone, plus thermostatic radiator valves. And E, a zonal control system with multiple thermostats and actuated valves on the radiators or the underfloor heating control. And in some cases, E can be retrofitted in an existing building. So some things to think about going back to the energy efficiency. Where is the thermostat? This could be quite important. Is it in a representative occupied space? Not over a radiator? Not in a hallway? Maybe not in the kitchen where you have intermittent heat sources from cooking, etc. Thermostatic radiator valves. They don't actually measure where you are. They're often near the floor, sometimes in a drafty space near a door. They have a dial 1 to 5. They're not calibrated to a temperature. So consider having a thermometer in the room as well, so you can self-calibrate the setting related to your comfort condition. Have different temperatures in different rooms. So living rooms should be warmer than bedrooms, for example. Halls and corridors can be at a lower temperature without suffering any discomfort. And the kitchen is generally an occupied space with heat sources in it, which can be at a lower temperature as well. Bathrooms may need to be at a higher temperature. You might have special considerations for babies, the elderly, those who are pregnant, and maybe some pets. Don't heat unoccupied rooms unnecessarily, but you may want to keep some heat in the space to avoid condensation issues. A zonal system may be the ultimate. So each room, and there's a little diagram illustrating rooms at the right with different temperatures at different times. Each room is a zone with a control thermostat and a time temperature schedule. Each heating device, underfloor or radiators, has a control valve, an on-off control valve, and often these systems have remote access via the internet, although this is, of course, isn't mandatory. You do need to think about what happens if there is a Wi-Fi or internet failure in your home. Does the system store the settings? Does it go out of control? How does it come back into control when power is re-enabled? Important questions that you need answers for if you're considering such a system. Now I'm nearly at the end, and I want to talk about monitoring performance. And I'm showing two sources of performance information. One is smart meter, and this is a real smart meter output on the right hand side of this slide, showing electrical and gas consumption in a particular property, and there are half-hour values of every day. And you can see what is happening and when the energy is consumed. And the diagrams on the left, the graphs, are showing the temperatures in controlled spaces in a multi-zone system. And you can see on the upper temperature chart that the temperature is set back at around 14 or 15 degrees at night and during the majority of the day, and it rises in the evening when people want to sit and watch television to a 19 or 20 degrees centigrade, and then it goes back down again automatically. This particular system also monitors the relative humidity in the space, which could be important to help you consider aspects of moisture content in the air and condensation. So, some conclusions. We all have a role to play in dealing with climate change and CO2 reduction. There are some quick, easy improvements. Maybe some grants and help will be available soon, again. Understand your system. Have a diagram. Make sure you have good maintenance and a properly tuned and adjusted system. Have effective control over that system and be very careful with its operation. We hope you found this useful. Please keep in touch with Zero Carbon Guildford and keep your eye on our Green Your Home zone down at Zero. If you want to get in touch for any further information, then please contact me, and here are my contact details, either by email or telephone. Thanks very much. I hope you found this interesting, and I look forward to seeing some of you again face to face when we have our next live forum. Bye for now.